Okay, in this problem, what we've got is given a situation, and what we've got to do is come up with a polynomial from it. So it's a little bit different because it's not given any thing much in terms of the function itself, but we're just given a description. So we've got to go through it carefully. The first part, px is monic, so that makes life easier because it's a monic polynomial. We've got a degree 4 integer coefficients, which is a nice thing as well, which means that they're all real, so we've got a few more things that can come into play. The constant is 2, so okay, we've told that we've got 1 0 at I and has rational zeros as well. So because it's got a 0 at I as well, that would give us a x minus I as a factor, but also x plus I would be a factor. Because I is a root, so is minus I. So because it was integer coefficients. So that starts to make life a little bit easier because we can play with that. Then we're told the sum of the zeros is a positive real number. And then find the factorized form. So, well, we start with that idea because we've got, as we said, I is a root, so minus I is a root, which means that when we expand that out, x squared plus I 1 is a factor. So that makes life a little bit easier. We're halfway there because we've got 2 of the roots. So what we have to do is try and come up with the other roots from what we've got. So because it's integer coefficients, we said we could have that. Our constant's 2, so they've got to multiply to give us 2. And the sum of the zeros was a positive real number. Well, those two will, like I plus minus I, will cancel each other out. So the other ones are a positive real number. So we keep that in mind as well. So, because if P and Q is a rational 0, Q is the factor of the leading coefficient, which is 1. So, because of that, Q must be 1. So, P is a factor of the constant 2. So, if that's the case, we've got rational zeros that could be minus 1, 1, minus 2, 2, minus 2. So we basically got two situations where we could have what we had before, I and minus I, and then minus 1 and 1 and 2, because they've got to multiply to give us 2. So it's either going to be minus, these are both going to be minus or both got to be plus, because it's constant of positive 2, because these two would give us positive 1, then these two would have to give us positive 2, these two would give us positive 2. So it's one of these two situations, but we've also told that the sum of the zeros is a positive real number. So if that's 1 and that's 2, that's minus 1, minus 2 for those. As we said, these two will cancel out, so the I and minus I in both of them cancel each other out. These will sum to give us 3, these will sum to give us minus 3. And it has to be a positive real number. So this one wins out. So this is our factorized form of our polynomial. So there we go. That's where we get this one from. So over the real field, we get x minus I, x minus 2 with the x squared plus 1, which is what we wanted the real number field. Because over the complex field, we were able to put it like that. But over the real field, we have to put it as x squared plus 1. So that's breaking it down, and if you can understand exactly what all those terms mean, we're able to put it together and get our factorized polynomial. In the next one, we're given asked to prove that 2 plus I is the root of the equation. Well, sure, we can do that. We can put that in and expand it out with a little bit of help from the binomial theorem to expand that out. And then collect all our terms to give us 0. That's got to take a lot of care to make sure it works out to be 0. So it's just making sure we get each term done correctly, and they will all cancel out to give us 0. And then we want to solve the equation completely. Well, if we want to solve the equation completely, well, we can know already that another root of this, because there are real numbers in the for the coefficients there, 2 minus I would be a root as well. So the polynomial of 2 minus I would equal 0. So we can write that as x minus 2 plus I and x minus 2 minus I as a factor of that polynomial. So given that situation, we can expand it out. We get x squared minus 4x plus 4 plus 1, which gives us that as our quadratic, which is a factor of this polynomial. And again, I've used that idea, so keep going back to that to expand that quadratic out. And then again, we could you can either go, we've got to divide that one into that one, so you can use polynomial division, or you could use it by inspection and say, well, I know because I've got the 5 there, it'd have to be minus 4, and then play around to get this middle term. But you can do it by doing a quadratic, the polynomial division to get this quadratic, and then we can write it as a multiplication of the two quadratics there, because that's solving it completely, and it's not going to be able to break down either because it's a minus 4 plus 2. So the discriminant of that one is less than 0. So we could get, well, unless you want to put it down in its complex form, you could do that, which we've done here, and we can break it down that way just by completing the square on that one. So it depends on how it wants it to be left. In question 5, we've got a polynomial. M and N are real numbers, and it's known 1 minus I is a root, one of the other two roots of the equation. Well, straight away we can go, if 1 minus I is the root of the equation, 1 plus I is the root of the equation as well, because they're complex conjugates. So the other root must be alpha, so we can use the idea, because we got the 6 there, of the product of the roots would be minus D on A, so minus 6 on 1, and we get the product of the roots. 1 plus I times 1 minus I is equal to 2. So 2A, alpha is equal to minus 6, so alpha is going to give us minus 3. So there's our third root there. And then from that we're able to get our values of M and N. Now you can substitute in the values there, get equations there. Or we could go with the idea that we're going to be able to use the sum of the roots equal to the minus m. So it gives alpha plus 2 equals minus m, so m would equal 1 there. Or then we can use the root sum of 2 at a time and be able to put those in, and that would equal n, and we're able to solve to give us n being equal to minus 4. So we can use different ideas. Like this is not the only way to do this one. It's probably the most efficient and the most elegant way to do this equation. So keep that in mind when it's not only one way to do some of these problems. We're trying to show you as many as possible. Show that z minus I is the root of this equation. Well, we can do that. So pi is a root. We notice it's a quadratic, and notice this time we can't go with the idea that it will appear in complex conjugate pairs. It's the fact that our coefficients are not real. They are complex numbers, some of them. So as long as we get one complex number as a coefficient, that rules out. So but substituting I in gives us 0. So because it's a quadratic, we really only have to work on the fact that, well, we're going to go find one more root. So the product of the roots, alpha plus I times I, would be equal to 1 on 2 minus I, because you see on A. So we've just done that. We can simplify that one to get 1 times a 2 plus I over 2 plus I to give us 2 plus I on 5, which means the value for alpha would be 1/5 minus 2/5 I. So there's our complex number there. So we're able to play with it that way, and we can manipulate it to get it round that way if we like as well. So because we've divided by I here, so you can see the working to get to the 1/5 minus 2/5 I, to get from that point to that point when you divide by I. So question 7 here looks at the idea that showing that 1 plus I is a root of that one. So again, we can substitute it in. We end up with being 0. So again, using the binomial theorem in this part. The other parts are a little bit easier without the binomial. You can do it without the binomial theorem. But 1 plus I is a root. And then solving this equation, well, we know if 1 plus I is a root, 1 minus I is a root. So we can form a quadratic to expand that out. So again, we know that we can do this method where we do it by inspection, where the z squared minus 2z plus 2, which we've already got, and we got z squared plus az plus b. So these numbers are going to be giving a situation where it's going to be equal to that. So 2 times b would be equal to 10. So that's where we get b is going to be equal to 5. That's nice. And equating the coefficient of z squared there. So we play around with the z squared because it's z times b, z squared times b, and 2z times AZ is going to give us this term in A squared, in Z squared, and 2 times Z squared is going to give us. So that's where we get all these coefficients there. Like the B, because it had B times Z, so which works out to be 5. And we get the minus 2A, minus 2 times A, and plus 2. That's going to be equal to C on A. You could have done that with Z cubed, or you could have done it with Z. You could have done it with any of those terms that you wanted, okay, except for the two end ones. And that allows us to work out with A and find minus 2A plus 7 is equal to 15. And then A is equal to minus 4. So we're able to work it down and get that other quadratic there. And then, being the roots for that one, okay, we're able to come down and find the roots of that quadratic there for us. So we had 1 plus I, 1 minus I, and from this quadratic we get 2 plus I, 2 minus I as the other roots. Question 8. Find the polynomial with real coefficients have 3i and 1 plus 2i as zeros. So looking at this one, then we know if 3i is a root, minus 3i is a root, and 1 plus 2i is a root, 1 minus 2i are roots as well. So basically, like, this should be a quartic equation, because we expand that out, we get an x squared plus 9, because that's those two are roots. Same with those two are roots, we get that quadratic. Then we're able to multiply that quadratic out and get our expanded form of our polynomial that we want for px. And question 9. We've got a quadratic equation here equal to 0, has integer coefficients. So if alpha plus square root of beta is a root, okay, show that alpha minus square root of beta is also a root. So, well, this is not too bad in that we can perform the quadratic equation on this one. So we get minus a on 2 plus or minus the square root of a squared plus b squared over 2. And we know a squared plus minus 4b is greater than 0 because it's got a root. So we know it's got that situation. So what we're basically saying is that we can get minus a on 2 plus or minus some number. So what we've got is a number plus or minus the square root of another number, which are going to be the same. So it's just a change by the plus and minus. We have our roots written in that form. So that's what we get: alpha plus square root of beta and alpha minus square root of beta, where alpha's minus a on 2 and beta's a squared minus 4b on 4. So we have that situation. So in the second part here, we have this situation when it's known to have only real roots, and further it's known at least one double root, express the product there as the factors with integer coefficients. So if that's the case, then we can say it's a double root, so we know that the derivative gives us an expansion, a derivative gives us that expression there, which we can start to break down. So we can work out that we can get x minus 1 there. So the derivative of that is equal to 0, but the function of 1 is not, and so that can't be a double root. So the x minus 1 going into that is not, that's not a double root, that's not the double root. So whatever happens from the other part must be the double root. So x squared minus 2x minus 4 gives us that division when we do that. So this must be from the double root, because from part 1 we go, any quadratic there must have, it's in that form, if it's got one root that's there, it must have the double root as well from it. So that must be x squared minus 2x minus 4 equal all squared from part 1 there. So that's where it's going to get us those roots for that one there. So that was a little bit tricky. Have a look through again at that one. So see how we go with that idea. If you've got more questions about these, we can ask and answer those in class.